तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome. In today's session we are going to be looking at a slightly different topic from the conventional idea of databases, and this change in topic occurs simply because the kind of users that the database is going to be is meant for is going to change. Until now we have had an implicit assumption that the users of who are going to be using the database are in some sense, if I can put it this way, are in some sense clerical users, in the sense that they are more interested in adding and retrieving data elements into the database as efficiently as possible. That means the users who are using this database are involved in the operational aspects of a larger system. For example, if we are thinking of let us say railway reservation, we are talking about how best can we design a database system for reserving a ticket, okay. Therefore what it means is whenever a new ticket entry is made, it has to be efficiently entered into the database, and suppose there is any modifications for a given ticket entry, it has to be efficiently modified. That means you should be able to efficiently search the given entry and make modifications at just one place if possible, and not many more places, and keep the overall consistency of the database intact, okay. And that is what we mean by operational aspects of a database system, or operational aspects of a system. It is the day-to-day operations. Somebody comes, gives a request for a reservation, and you enter the request, you reserve a seat for him and give him the ticket, and or cancel it something, or ask for concessions or whatever and so on. But there are other kinds of users who use the database system as well, and specifically we are talking about users who take strategic decisions, okay, in addition to or in contrast to the tactical decisions that are taken by the operational people, that is the folks sitting in front of let us say ticket counter take very tactical decisions. How efficiently can you perform your operations? But then there are a variety of strategic decisions which is the best way, which is the best location for me to place my next railway reservation counter, which part of the city has the most people travelling by trains, or which part of the city has the most people travelling by first class AC, or which part of which time of the year is the best for me to offer concessions on second class sleeper, something like that, right. So these kinds of strategic decisions are of a qualitatively different nature than the tactical decisions that are taken for operational issues of any system. And but if you watch closely, it is the same which are fed and retrieved in operational situations. It is the same data that that is required for making strategic decisions as well. If you have to make strategic decisions about, let us say, which is the best location for me to open my next open the next reservation, for that we need a lot of information about what is the from what addresses are people coming and booking tickets where, right. If somebody comes from area A and books tickets in area B, and assuming that area B is the nearest reservation counter, and how do, and the address information will in turn show me that because there are a lot of such people coming from here to there, it probably makes more sense for me to open a next counter here and so on. Okay. So we will see in the next few sessions how the whole aspect of database design changes when the usage scenario changes from an operational data usage to a strategic decision making usage. So that brings us to the topic of data warehousing. Data warehousing, as you might understand the term warehousing, a warehouse is where you keep your inventory stock, right. That is where you have stocks from several different sources or going to several different sources, and you're essentially talking about a large number of stocks that are maintained in the warehouse, and a warehouse is typically of strategic importance. If you take up let us say some kind of a civil engineering project, the location of your warehouse, for example, is of prime importance, depending upon because there which depends upon several factors, like say what is the cost of transportation, logistics, coordination and so on. Suppose you're handling a large infrastructure project somewhere, let us say building a flyover or something like that, having the location of your warehouse in a way that is easily accessible with possible cost constraints is probably one of the most crucial strategic decisions that can be taken. In an analogous sense, a data warehouse is a warehouse of data elements that have been captured from different operational data sources, so that you can so that this whole set of data elements becomes is of strategic importance. You can take strategic decisions based on the data elements that you have gathered, and which leads us to the next term in the slide here, which is called as OLAP, or online analytical processing. That means we are looking for requests or queries that are of an analytical nature rather than an operational nature, or what we call as a transactional nature. We have talked about transactions quite a bit now, and we are now looking into analytical queries, where queries in turn help in strategic decisions. By itself is a vast subject, and there are several research papers that have been written and several commercial implementations that have been implemented, and the huge amount of interest in data warehouses. However, in this course we shall probably be touching just a small part of this vast ocean of data warehouses, and the way this we have partitioned this our exploration into data warehouses are in three parts, as shown in the slide here. In the first part, we shall be looking into an important difference between OLAP, that is online analytical processing, versus the online transaction processing that traditional databases are geared towards. Issue in data warehousing, namely that of data cleaning and data integration. The next two parts deal with the warehouse core itself, where we are talking about the data models that go inside the data warehouse, and what are some of the thumb rules which go towards data warehouse design. We will also look at some kind of index structures for data warehouse based on the data models that we study, and see how they differ from databases, like say B plus trees, or B trees, or hash based indexes, or something like that. When we are talking about data, we can essentially divide data into two kinds of data. Essentially I have called them as operational data, and the next slide shows calls it as historical data. That is, operational data can also be considered as data that works within quotes. That is, data that is involved in the operation of a particular system. For example, if you are if you want to withdraw money from your account, you need data about your account, your account number, your PIN number if you are using an ATM, if your account balance and so on. All these data elements are all operational data elements because they are crucial, they are necessary for performing the operation of withdrawal of money, right. And what are the characteristics of operational data? Operational data are subjected to frequent updates and queries. You could be withdrawing money almost every day, or some kind of operations would be happening on your account almost on a daily basis, and so there would be some kind of queries or updates happening quite frequently to your to the database that is maintaining your account information. Therefore, we saw in the sessions on normalization and functional dependencies, we saw that in order to make the process of updates and queries efficient, we need to normalize the set of data elements. That is, we need to normalize so as to prevent any kind of redundancies occurring in the data, and also to prevent any kind of update anomalies. Suppose I update a record in some place, and there are redundant copies of this this same record of some fields, then I will have to update all occurrences of these fields. So in order to minimize update anomalies, we essentially normalize the set of data elements, and a set of tables that are normalized are essentially fragmented. Because a given data element, let us say your account information may require several information, something like your account number, name, address, branch location, balance, transaction history, and type of account, and so on and so forth. And because they are normalized, the set of all tables are fragmented in different places, and the operational data is usually of local relevance, which is kind of emphasized in the which should kind of be emphasized. That means it is very unlikely to expect, let us say that you have opened an account in Chennai, and you go to Delhi and want to access your account. It is unlikely to expect the account information that you have opened in your bank in Chennai to also be present in Delhi. It has to be queried in Chennai, and your request has to be routed through to Chennai, and then it has to be queried here, and the result sent back to Delhi. So operational data is usually of local relevance. Wherever the data is, it is relevant there in the geographic location there. And the kind of queries over operational data are also what are called as point queries. What is a point query? A point query is something like asking something about asking a query about some individual tuple. For example, what is the balance in your account with account number so and so, or what was the last set of 10 transactions that your account had. Therefore, what is happening here is that there is a particular point or a specific tuple that is the key where your account number in this case, where which is being used to access all relevant information for the operationalization. On the other hand, there are you can think of another kind of data called as historical data, or also called as archival data. That is data which are archived over a long period of time, over a long period of different operational data sets. Okay, it's a long set of operational data sets, and it is these kinds of data which tell us something. That is, it's also called as data that tells. They tell us something about the overall trends of operationalization that is happening. That is, suppose I have data collected over from all railway reservation centers for the past 10 years, it can tell us about trends as to which are the peak times in which people travel, what kind of people travel in what kind of or make what kinds of railway reservations and so on. I mean, people having what kind of salary range travel in what kind of classes, sleeper classes, AC or whatever and so on. So it's that data that tells us something about the larger system which is using the data set. And as you can see here, the kind of updates that this data set undergoes is quite infrequent in nature. It is not like every day that you are going to get historical data, you have to get historical data over a period of time. Therefore, you collect historical data, let us say once in 6 months or once in a year, or something of that order. So it's a very infrequent updates, but what is more important here is that updates are not all that important, that is they happen very infrequently, so we can take care of them whenever they happen, but it is the queries that are more important, that is analytical queries require huge amounts of aggregation. What is the average age of the person traveling in second class sleeper? If you want to calculate that, it needs a huge amount of aggregation over a large data set based on all different second class sleeper tickets that have been sold, right. And this is an integrated data set with a global relevance. We are not it usually does not make sense to look at trends in a given operational data source. It does not make sense to say what is the trend in this particular reservation center. I mean it usually would be very small compared to the larger set of all different operational data sources. And the performance issues in managing historical data occurs mainly in query times and not in update times, because of course updates are far more infrequent than queries, and queries need to access a large amount of data, and you have to perform a number of aggregate operations before being able to return the query, and they have to return it in an online fashion. That is why it is called online analytical processing. You have to return it in return query results in a interactive response time, that is the user should be sitting in front of a terminal, and the interactive response time is usually of the order of maximum a few seconds, and you can't expect the user to be waiting for a large period of time after giving the query. Let us look at some examples of transactional data and historical data. Transactional data or operational data are those kinds of data elements that are handled by systems that are called as OLTP systems, or online transactional processing systems. That is these systems which maintain transactions and handle different transactional activities in the system. Now what are some examples of operational queries? Something like, say, what is the salary of Mr. Mishra or what? So it is it's a point query, as you can see here, that is you find out the employee number of Mr. Mishra and then get the salary field, and that's it. Or what is the address and phone number of the person in charge of the supplies department? Again, it's a point query, that is it's just a question of following different references. Find the supplies department and look up the set of managers, and given the supplies department ID, look up who is the manager's ID, and then given the manager's ID, find the address and phone number of the manager, and so on. Okay. So these are some kind of typical analytical queries, typical transactional queries, which we have seen quite often now. That is, we have seen how to specify these queries in SQL, how to optimize these queries, how to create transactions around them, and so on and so forth. Queries shown in this slide. How is the employee attrition seen changing over the years across the company? As you can see, this kind of query is qualitatively different. It's qualitatively in a different caliber than the kinds of queries which we saw in the previous slide. If you want to answer this query, let us say, how is the employee attrition seen changing over the years and across the company? It's not a question of accessing one particular record or one particular tuple. You need to look at employee attrition information across the company and across the years, and then look for trends, saying, okay, it is increasing, it is decreasing, and so on. That is, you have to find out some aggregate employee attrition information across the company, and then plot it against the years and see how it is changing. Or something like, is it financially viable to continue our manufacturing unit in Taiwan? So it's a pretty vague query, right? What do we mean by financial viability? How do we calculate financial viability? Profits against costs and so on. So how do we know that we are incurring more profits than costs, or we are gaining more profits than the cost that we are incurring? It's not quite easy to find that out. That is, you need to be able to aggregate a number of different information sources and then say, okay, profits are generally more than the costs and so on, right? So these are the kinds of queries which are of an analytical nature and typically of interest for strategic decision making, managers who perform strategic decision making. A data warehouse is an infrastructure to manage such kind of historical data, and it is designed to support OLAP queries involving very gratuitous use of aggregations, aggregated queries and so on. And it's not just a queries, there's also a number of post retrieval processing, also called as reporting, which is just as complex or possibly more complex than the query retrieval itself. That is, I have gathered huge amount of information about all possible profits and costs from all possible centers and so on. How do I project this information? How do I give out all this information to the decision maker, which is again quite involved in itself. So this slide shows the schematic diagram of the overall architecture of a data warehouse. Data warehouse, as we saw in the previous slide, is meant for managing historical data. And where do you get the historical data from, or how do you first of all come out with the historical data? Historical data you essentially obtain from all the operational data sources or the OLTP units, right? So you have several OLTP units for your organization. Whenever you are thinking about an organization here, think of a large organization, something like say the Life Insurance Corporation of India or the Indian Railways or something like that, where they have number of different units, each of them having their own databases, each of them handling their own accounts, each of them handling their own reservations or and transactions and so on. And from each of these OLTP units we obtain a huge number of operational data elements every day. Right, every day there are number of people traveling in trains and from number of different and they would have booked their tickets from number of different sources. Now all of these data, operational data, are then subjected to a data cleaning and integration process. We shall see shortly what is meant by data cleaning and integration. There are a huge number of possible inconsistencies or possible sources of what we call as dirty data that can exist in the OLTP sources, and we will see what are these sources of dirty data that can exist and how we can clean or what's also called as data scrubbing and so on before we are able to present it as historical data. Now once operational data is subjected to data cleaning and are integrated across all of these OLTP sources, we present them as historical data into a data warehouse. That is, a data warehouse would already exist, and you just integrate this set of data into the data warehouse. You just update the data warehouse with this set of data. There is also a notion of data marts which is probably of interest here, at least to look at the definition. Whenever we talk about data warehouses, we look at them as a collection of different data marts. That is, a data mart is historical data about one specific kind of one specific segment or one specific OLTP segment. Suppose you are considering, let us say, again take the example of Indian Railways, okay. Let us say we have one segment called express train reservations, okay. That is one data mart. That is, suppose we are interested in strategic decision making only about express trains, or maybe let us say Rajdhani Express or something like that, all the super fast trains. Okay, so all of the historical data that we gather about Rajdhani Express would go into the data mart called Rajdhani Express, that is of all Rajdhani Expresses across across the railways and over a period of time and so on. So and the data warehouse is usually seen as a collection of these different data marts that feeds into the data warehouse. And data marts are also seen as small warehouses that where you can in some way you can support all activities that you support on a data warehouse also on a data mart, and but these are within a given segment. Now let us expand this this system or this box on data cleaning and integration and see what happens inside that. As we earlier mentioned, we obtain data from different OLTP data sources, operational data sources that feed into the data warehouse. Now can we or what kind of we are able to before we are able to integrate operational data sources or before we are able to populate the data warehouse from the operational data sources. Operational data sources, as we have seen, are mainly meant for data that works, that is as long as the as long as the data is sufficient for the operation to be performed, it is good enough. It is characteristic of operational data is that operational data is of local relevance. It's usually relevant, that is data in an operational data source is relevant only locally. However, when we are talking about historical data in a data warehouse, there are two different things that that you have to is the one is that because we are using different kinds of data sources, we should have a uniform standard of data representation and semantics across all of these different data sources. And secondly, we should remove any kind of duplicate information that are present in these data sources. Suppose you have suppose you have an suppose you have opened an account. Let us say let us again take the running example of Indian Railways. Okay, now suppose you have opened an account for booking tickets over the web. Okay, now you have booked a few tickets over the web, and then you have not booked tickets for quite a significant period of time, in which time you forgot your username and password. And you forgot that you had ever opened an account here, and then you go back and open another account for buying tickets over the web. Now as you can see, if these two accounts, the behavior in these two accounts are considered different, are considered to be from different users, then it will give us erroneous information or erroneous aggregate information for strategic decision making. It is important that it is important for the for historical data that these two accounts should be clubbed, or we should recognize that these two accounts belong to the same user and then club them together whenever we are performing any kind of aggregate queries. So let us see what does it entail to do all this, or what are the kinds of complexities that we encounter in performing this kind of data integration and cleaning and so on and so forth. The general model of data integration and cleaning is shown in this slide here. As we saw in the previous slide, these are the different OLTP data sources which feed into the data cleaning and integration unit, and usually we have opened the box which was a black box here. Now we have opened the box and we see that there are usually two different units here, the data cleaning unit and the data integration unit, and the process by which data flows through this unit is not a unidirectional process, that is you garner data from these OLTP data sources, pass them through data cleaning, pass them through data integration, and also perform some kind of a back flushing, that is you have back into the OLTP databases itself. We'll look at some examples which tell us what it means actually. And once the data is integrated, it is fed into the data warehouse, and based on queries in the data warehouse or updates in the data warehouse, you get a feedback from the warehouse itself which tells how is it that you should perform your cleaning, what is important for the data warehouse. And cleaning essentially means that we have to change whatever is important for OLTP to we have to change representations from whatever is important for OLTP to representations where whatever is important for the data warehouse. So let us look at data cleaning or the DCU in a little bit more detail. As the name suggests, data cleaning performs cleaning operations on data sets, that is data sets that contain dirty data. What is meant by dirty data? That is what are the different sources of dirt. I am talking about dirt within quotes, so that that one can encounter for given operational data source. There are several different possible sources of dirt that requires cleaning to be performed. The first kind of the first kind of dirt is what is called as lack of standardization. For example, because you have different branches, different reservation centers at different cities, there could be multiple encodings. One of them could be using ASCII based systems, one of them could be using Unicode, one of them could be using EBCDIC or something or the other. So there could be multiple encodings, multiple locales, multiple languages in which data is represented, and you should be able to onto a standard encoding or language or whatever. There could be spurious abbreviations. Somewhere somebody writes Mahatma Gandhi Road in part of an address, and somebody else writes MG Road. Now we need to be able to recognize that MG Road is the same as Mahatma Gandhi Road. So when we are talking about when we are answering a query like how many people come from in and around Mahatma Gandhi Road or live in and around Mahatma Gandhi Road who buy tickets, we should be able to we should be able to search both MG Road and Mahatma Gandhi Road for because they are the same. And similarly there could be semantic equivalence. MG Road and Mahatma Gandhi Road, probably you can write an intelligent algorithm that will see whether Mahatma Gandhi Road is an expansion of MG Road and so on, and you could kind of fairly well find out that okay, this is a spurious abbreviation and so on. However, what if there are semantic equivalences? Chennai and Madras. Some people may use Madras for the city name, and some people may use Chennai, and because we are talking about historical data, note that which is important here, that is at one point in time officially Chennai was called Madras. So even in official documents you would be using the name Madras, but then again it would have become Chennai. Now you should be able to correlate or say that these two are the same, and no intelligent algorithm can do that. You need extra knowledge in addition to the data sources. You need knowledge about the overall environment, the governmental policies, the standards and so on, in order to be able to identify these duplications. Similarly, there could be multiple standards. There could be one data source which could be using the metric system, while somebody else could be using miles and feet and so on and so forth. So so somebody might in one data source might have said 1.6 well 1.6 kilometers is the same as 1 mile. So 1.6 kilometers, and somebody else might say 1 mile and so on. There could be other sources of dirty data like missing, spurious or duplicate data. For example, the age field of an employee could be missing, and which will hamper my query of what is the average age of an employee or something like that, or what is the correlation between the age of an employee and the attrition and the probability of attrition and so on and so forth. Okay, or there could be incorrectly entered sales values, or incorrectly some typographical errors and so on, or there could be duplication of data sets. And duplication appearing in different forms. For example, take a look at the last example. A person called L. Balasundar would have registered in one, would have bought a ticket in one reservation center, citing his name as L. Balasundar. The same person would have gone to a different reservation center and bought another ticket at some other point in time, citing his name as B. L. Sundar, and with the same address and the same phone number and so on and so forth, and we should be able to detect such kind of semantic duplication. That is, there is duplicate data that is occurring in at different data sources, but not in the same form. That is, the name has changed, or something has changed, but semantically there are still duplicates. There could be other sources of dirty data, like inconsistencies, incorrect or inconsistent use of codes. Let us say in one of let us say in one reservation center, the gender of the person who is reserving a ticket is maintained as a character, either M or F, and in other reservation center it is maintained as 0 or 1. It is just the different standards that each database designer has designed for each center, and this is especially true if this has evolved over time. Let us say reservation center number 1 could be using a historical database that was designed, which has not changed because of cost considerations, and the new reservation center is using a new database system that has been redesigned, which is termed to be more efficient and so on and so forth, but which uses different codes for the same data element. And there could be codes with some outdated meaning. Let us say third class sleeper. Because we are talking about historical data, it is quite possible that we encounter some data about third class sleepers which no longer exists in railways today and so on. And there could be inconsistent duplicate data. That is, there could be two data sets that are found to belong to the same person. We have reasons to believe that it is the same person, but he has given two different addresses in these two different sources and so on. How do we detect such things? And other kinds of inconsistencies, like inconsistent associations. That is, let us say one department provides a particular kinds of says that the sales have been so and so and so on, but it does not add up to the total sales figure that has also been provided. So associations across different data sources may be inconsistent, and there could be semantic inconsistencies. Somebody might have typed February 31st in a date. So what does that refer to? Is it February 31st or March 1st or March 31st or what? Or integrity violations in referential integrity, like referential inconsistency. There is let us say 10 lakh rupees sales reported from a unit that has actually closed down, which is not even there, and so on. So several kinds of these sources of dirty data crop up in practice, and perhaps cleaning or data cleaning is perhaps the single biggest research problem that is still kind of open in the field of data warehouses, because there is no single thumb rule for data cleaning. We can't just say all data is passed through one kind of data cleaner and it will be cleaned, because there are several sources of dirty data that can occur, and there is no single way of cleaning them. So what are the issues in data cleaning? It is automated. It's quite difficult to automate for the computer to learn by itself that let us say Chennai was called Madras or Burma was called Myanmar or so on and so forth. and the thing is we do not even know whether the data cleaner is performing correctly, which is what is called as GIGO, or garbage in and garbage out. Suppose we give some garbage and we do not have correct rules, we just give some junk data and it just gives some junk output. We do not know whether it has actually cleaned or whether the output is correct or not, and it is quite hard to verify the cleanliness of the output data. And data cleaning requires considerable knowledge that is tacit. For example, 1 kilometer or 1.6 kilometers equal to 1 mile, which we know, but it is kind of a tacit knowledge, it is not explicit knowledge, and which goes beyond the purview of the database. Like Chennai was called Madras, so you should know data about governmental policies, you should know data about geography, you should know some knowledge about geography, governmental policies, metrics, and so on and so forth, which has to go into the data cleaning unit. So it's not possible to design a data cleaning unit in a way which kind of paraphrased as one size fits all, or which says that this is the data cleaning unit and this will work for any kind of data in any context whatsoever, and so on. And the data cleaning complexity increases as we increase the number of data sources, or increase the history span that we have taken up for cleaning this. What are some of the steps in data cleaning? How does a typical data cleaning process look like? Essentially there are five different steps that go into a data cleaning process. Firstly, we start with data analysis. Given the set of different OLTP data sources, we start by analyzing them and look for certain kind of metadata, that is what can we learn about the kind of data that we have, and then give all this metadata back to the user or the data cleaner. Okay. Now the user in turn will now specify a set of transformation rules, that is, if this is the kind of dirty data, this is how you have to transform it into clean data, and so on. So so the user specifies a set of transformation rules that are performed either at the schema or data level, which transforms dirty data into clean data. We then verify the rule by running them on test data sets, that is some kind of sample data sets, and then we incorporate the transformation rules into the data cleaner and then perform the data cleaning process. So once the data cleaning process is performed, we usually also perform what is called as a backflow, that is, we repopulate the data sources with clean data. For example, suppose you have seen that Chennai and Madras are used interchangeably in the OLTP data source, we see to it that, or we perform a backflow so that it's all either Chennai or Madras in the OLTP source itself. That is, there's some kind of standard in the OLTP source itself, which is called as backflow of data. We shall not be looking into great detail into how each of these transformation rules are performed, but let us have a look at some specific or some typical examples of how dirty data can be cleaned. For example, how do we search for illegal values within what is the strategy for checking for illegal values? We could use some kind of a max min or mean deviation or cardinality criteria, that is, slide a window through your data source that contains a max min limit for your for the particular data value. Whenever a given data value is lesser than the min or greater than the max, you know that it's a illegal value. So similarly, mean and deviation or cardinality and so on and so forth. And spelling mistakes, how do you look for spelling mistakes? There's some techniques what are called as n-gram outliers, and n-gram is essentially a collection or a sequence of n letters that form different words. For example, suppose I take a 3 gram, okay, let us say hashing, okay, I perform a 3 gram transformation on hashing, then I get several different 3 grams. HAS is a 3 gram, ASH is a 3 gram, and SHI is a 3 gram, and HIN is a 3 gram, and so on. So I get different 3 grams. Then what we do is we cluster all these 3 grams based on their occurrences, and we see if outliers in these clusters, that is are there any n grams which stand alone without belonging to any cluster. Most likely these outliers are going to be spelling mistakes, and that's a strategy that's generally used for checking spelling mistakes. Similarly, lack of standards, that is compare value sets from a given column across different tables and see whether they are using the same standard or so on. And duplicate and missing values, that is compare the number of rows with the cardinality of this particular column. So you will find out if the number of rows does not match the cardinality, you see that there could be some kind of missing values or null values in this. Okay. So let us look at 1 or 2 algorithms in slightly more detail, which can give you an appreciation of the kind of complexity that it takes, or the kind of techniques that are used for data cleaning. A simple algorithm for duplicate elimination, what is called as a hash merge algorithm. If you remember the storage structures session that we covered, you know what is meant by hashing, right? That is given a particular tuple, run it through a hashing function so that it is mapped onto a given bucket. Okay. Now what can we say about hashing across different tuples? Duplicate tuples, that is tuples with duplicate. Okay. Therefore elimination of duplicates now reduces to searching within a bucket for looking at any duplicate values and then eliminating them. So right. So here is an illustration of the hash merge algorithm. Let us say there are 4 different records like this, and this is the hash key, that is the name and address of the person. That is, we want to eliminate duplicates as far as person information goes. So as you can see, KJ Amit and 50 LVL road, both of them map onto the same bucket, and these map onto different buckets and so on. So you just compare within a bucket and then eliminate duplicates. There is another technique called sorted neighborhood technique. This is mainly used for misspelling or detecting misspellings in data sets, and the sorted neighborhood technique is given by the following algorithm shown in this slide here. First of all, identify what is the key. As in the previous case, we identified that name and address is the key. Okay. So identify what is the key within a given tuple. Okay. Then sort the table based the table based on the key. You can see that all duplicates will cluster together, right. Similarly, all misspellings, there is a high likelihood, it is not that they will be, but there is a high likelihood that all misspellings will also be clustered together, that is will be quite close to the actual spelling that has to exist, right. That is, for example, if KJ Amit has become, let us say, KJ Aman or something like that, AMAN. So it's Aman is still quite close to Amit, that is assuming that we are sorting tens of thousands of records, misspellings would still be quite close to the real spelling. Then you slide a window, that is take a set of n rows and keep sliding it through the database to see if there are any misspellings, and then merge the misspellings, and we have to make multiple passes until there are no more merges of records. So here is an example again where this is used for duplicate elimination in addition to misspelling detection, where given this table here, it is sorted like this here, and given a window of size 3, we see that there are duplicates within this window, and we start eliminating them. And the last algorithm that we are going to see for duplicate elimination and also and also for misspelling detection and so on, what is called as the graph based transitive closure for this algorithm is more of a improvement over the sorted neighborhood algorithm, where it basically reduces the number of passes. The idea behind the algorithm is based on the notion of transitivity and in an equivalence relation. For example, if let us say records R1 and R2, okay, we see that R1 and R2 are duplicates, okay. So and we establish a relationship that R1 is a duplicate of R2 and so on, and then we find that R2 is a duplicate of R3, okay. We can definitely infer that R1 is a duplicate of R3 as well, right, because the duplicate is duplicate of relationship is a transitive relationship. If A is a duplicate of B and B is a duplicate of C, then A should be a duplicate of C. What this means is when sliding the window, once we have established that A and B are duplicates, there is no need for us to compare A and C and so on, okay. So that is the essential idea behind the graph based transitive closure. This slide here shows a schematic example where there are 5 different records, and in a naive sliding window sorted neighborhood protocol, we start by comparing R1, R2 and R3, then R2, R3 and R4, and R3, R4 and R5. We are just sliding it with a window size of 3. However, when we slide R1, R2 and R3, suppose we see that R1, R2 and R3 are duplicates, okay. So R1 is a duplicate of R3 and R2 is a duplicate of R3 and so on, okay. Now there is no need to compare R1 and R2 with R4 and R5. It is sufficient if we just compare R3 with R4 and R5. So that is the general idea behind this algorithm, which can reduce the number of passes in eliminating duplicates. The next topic that we come in the data cleaning and integration is the issue of integration itself. That is, there are different OLTP data sources from which we are getting data, most of which have different kinds of inconsistencies and sources of dirty data and so on, and we have to clean them and so on. But after we clean them, we have to integrate them under a common banner, okay. And this integration can occur at 2 different levels, which are shown here as data integration and schema integration. That is, schema integration entails forming an integrated schematic structure based on the set of all disparate data sources. That is, you have data sources from counter A, counter B, counter one common schematic structure. And data integration essentially entails cleaning and merging data from these different sources, that is eliminating duplicates and merging all of them under this schematic structure. Let us briefly look at what are the issues or what is the complexity now in schema integration as well, and it is not as simple as it looks like. Consider the following schemata that is shown here, okay. There is a schema that let us say one of the OLTP sources use, which is called which uses a table called cars, okay. And the cars table has different fields like serial number, model, color, stereo, glass tint and so on and so forth. Everything is in one table. On the other hand, another retail center, let us say, okay, uses 2 different tables for the same information, and look at how these tables could be different. First of all, there are 2 tables rather than just 1 table. Then the names are different. All these names are in German and these are in English. So cars are called autos, and serial number are called serial number and something. Color is called Farbe and so on. So it's not just the structure is different, the names of each of these fields could be different, the data types could be different and so on, right. So there are several different challenges that we have to face when performing schema integration, that is there are naming differences, there are structural differences, data type differences, semantic differences, missing fields and so on and so forth. The generic architecture of a schema integrator is shown in this slide here, where it basically consists of two specific stages. One is the lowermost stage is what is called as a wrapper or an extractor, that is given a particular schema, the extractor maps all given schema into a standard schema set. That is whether it is color or whether it is cars or autos or whatever, it maps it onto a common schema set, and then the mediator constructs the overall schema set or rather looks at this as a federation of different data sources having the same schema, and then handles query based on or constructs the data warehouse or handles query or whatever. So the difference between a wrapper and an extractor is that an extractor essentially physically extracts data, creates a schema and physically extracts data from the data sources according to the schema, whereas the wrapper is just a logical wrapper. Similarly, a mediator is a logical mediator, while a constructor physically constructs the data warehouse from all the extracted data sources. So there are different tools for data cleaning and integration, and as I said, there is no common tool that can fit all possible requirements, but there are several tools that can make the life easier for this thing. So here are some examples, say DF power or ETI star and SSA name and so on and so forth, right. So let us summarize what we studied in this session. We looked at the important differences between OLAP and OLTP queries. What is the difference between analytical queries and transactional queries? What are the characteristics of OLAP of a data warehousing system, where you take data from different OLTP feeds and take them through data cleaning and integration phases before populating the data warehouse, and then of course there is a feedback and backflush and so on, and this itself is a major issue within itself. So that brings us to the end of this session.